In this lesson, we're going to be looking at another analytical way to evaluate a limit. It's called the squeeze theorem. Let me start by graphically showing the idea behind the squeeze theorem. So let's draw a graph here first of all. If we had the graph of some function here, let's call this, let me change the colors here so we can distinguish between our graphs. Say we have this graph here. And we're trying to find the limit of this function. We'll call this y equals h of x. We're trying to find the limit of this function as x approaches c. So let's say this is x equals c. So we would see that the limit was here. Now, if we looked at a function like y equals the sine of x over x, let's say we tried to find the limit of the sine of x divided by x as x approaches c. Now, we would see that if x approaches 0, we'd have a difficult time trying to evaluate that limit because it would give us 0 over 0, the indeterminate form, but we wouldn't be able to use one of the techniques that we have learned. So this is the idea. We have some limit. We don't know how to find this limit of h of x. So what we're going to do is we're going to look at trying to find another function that is always greater than h of x. Let's say we have this. Let's call this f of x. And we know how to find the limit of f of x as x approaches c. And we can find another function. Let's call this one g of x. So we have y equals g of x. And we do know how to find the limit of g of x as x approaches c. We could build an inequality here that says h of x is always less than or equal to f of x. By looking at the graph, we can see that that is true. And h of x is always greater than or equal to g of x. We know how to find the limit of g of x as x approaches c. We have a function here where we can evaluate that limit. So let's say we found that to be L. And we know how to find the limit of f of x as x approaches c. And we find that to be L. Since h of x is always between g of x and f of x, we have squeezed that limit to be between those two, but if they both equal L, we know this limit also would have to equal L. That's the idea behind the squeeze theorem. We have a function h of x. We don't know how to find the limit of h of x as x approaches c, but we can find a function f of x. We know how to find the limit of f of x as x approaches c. We know that equals L. We can find another function, g of x. We can find the limit of g of x as x approaches c. We know that equals L. Therefore, we can conclude that the limit of h of x as x approaches c must also equal L. That is the squeeze theorem. That's the whole idea behind the squeeze theorem. Let's look at this limit. We have the limit of the sine of x divided by x as x approaches infinity. Now, if we tried to use like the direct substitution method and said, well, if I looked at values of the sine of x as x gets larger and larger and larger, well, we know the sine's an oscillating function, and so as x gets larger and larger and larger, that limit would not exist. So what we're going to try to do is we're going to look at the sine of x. If we looked at the graph of the sine of x, we know it looks like this. We know the maximum value is 1, the minimum value is -1, so we know the sine of x has to be less than or equal to 1, greater than or equal to -1. Now, with this inequality, we're going to divide each interval by x. So we would get the sine of x divided by x in the middle interval. Now we know if we divide an inequality by a negative value, we have to switch the inequality. So how can we be sure we don't have to switch these inequalities? Well, x is going off to positive infinity. We're concerned when x is getting larger and larger and larger in the positive numbers. So we can be assured that x is going to be a positive value. We don't have to switch our inequalities. Now we're going to take the limit of each one of these intervals as x goes to infinity. We do know how to find the limit of -1 over x as x goes to infinity. As the denominator gets larger and larger and larger, that quantity is going to be getting closer and closer to 0. So this is approaching 0. And likewise for this limit, as x gets larger and larger and larger, say we have 1 over 10, then 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, that's getting very, very close to 0 also. So that is also approaching 0. So we can conclude that the limit of the sine of x divided by x as x approaches infinity must also equal 0. Here's another problem. So this one we're going to apply the same logic. We're going to first of all look at the cosine of 1 all over x squared. Now that will be bounded between 1 and -1 also. So we're going to multiply each interval by x squared. Then we will take the limit of -x squared as x approaches 0. And the limit of negative x squared as x approaches 0 equals 0. And the limit of x squared as x approaches 0 is 0. Therefore, we can conclude this limit also equals 0. Another limit. So the cosine squared of 2x. We know that the cosine of 2x would be bounded between 1 and negative 1. Now, cosine squared of 2x means this. So the inequality here, we could change that value because this cosine of 2x squared can never be negative because that quantity is being squared. So the minimum value it could be is 0. So we would have 0 is less than or equal to cosine squared of 2x is less than or equal to 1. Now we're going to divide each one of these intervals by 3 minus 2x, but we're going to do it in 2 steps. First of all, let's divide by the negative 2x. Well, here we are dividing by a negative value because x is going off to infinity, so we would have to switch our inequality signs. I forgot to reverse that inequality sign. Now, if we added that 3, so if we take the limit as x goes to infinity, we know the limit of 0 as x goes to infinity is 0. Here I don't have this written correctly. So let me rewrite that better. And this should be as x goes to infinity. So we have the limit as x goes to infinity, cosine squared of 2x divided by 3 minus 2x. And the limit of 1 over 3 minus 2x, as x goes to infinity, the denominator is still going to get larger and larger and larger in the negative direction, but is still going to 0. So we can conclude that our limit equals 0. Another limit. Let's take a look at the sign of 1 divided by x. Now we know that's going to be restricted from -1 to +1. And we're trying to recreate this expression over here, so we're going to take and raise each side to the base e. Then we will multiply by an x squared. And if we take the limit of each interval now, this limit here could be written as x squared over e, but as x goes to 0, we can use direct substitution. We get 0. And this limit here, again, direct substitution, because e is just a number, we'd have 0 times e, 0. Therefore, we have found our limit. Need to cancel that. Ah, come on.